Cryptography and Network Security. This course is for 4th BTech first sem. Myself G. Prashanti, Vignans Nara Institute of Technology and Science, Department of Information Technology. So in today's class we are going to study about some asymmetric key crypto systems. Okay, already in previous class we have gone through what is an asymmetric key crypto system, and similarly we have seen the knapsack crypto system. So in today's class we are going to study the other crypto systems. So here the first we are going to study is your RSA crypto system. Okay, so this RSA crypto system is an asymmetric key crypto system, and this is the most common public key algorithm. This is the most commonly used public key algorithm. Okay, and it is named after their inventors like Rivest. Okay, so these are the three persons, Rivest, Shamir and Edelman are the three persons who have developed this RSA algorithm. Okay, they have named the algorithm after their names, that is Rivest, Shamir and Edelman, that is nothing but the RSA. Okay, so this is the process of the RSA encryption. Already we have said in every public key crypto systems we are having three modules. The first module we will be having is the key generation. Okay, so first module we will be having a key generation, where in the key generation, so here we will be generating like public and private keys. Okay, whoever the receiver likes, the receiver will be generating the public and private keys by using the key generation algorithm, and then he will be keeping the private key as secret and he will be announcing his public key. Okay, so here this whatever the Bob by using that key generation algorithm, he has generated his public key and private key. Okay, so here the public key is E, N and the private key is D. Okay, and then what he will be doing, he will be announcing his public key and then he will be keeping the private key as secret. Okay, so here for doing a secure communication, what the sender has to do is that suppose Alice is the sender, what she will be doing is that she will be encrypting the message. Okay, whatever the message or plain text the sender wants to send to the receiver, the sender will be encrypting the message with the public key. Okay, so here the formula for encrypting the message is C equal to P to the power of E mod N. Okay, where this E and N are the public keys and P is our message. Okay, P is our plain text, or we can say P is the message that we want to communicate. So you have to use P to the power of E mod N to get the ciphertext. Okay, and after getting that ciphertext, the sender will be sending the ciphertext to the receiver. The receiver has to decrypt it. Okay, so here what the receiver will be doing is that since he knows the private key, so by taking that ciphertext C to the power of D mod N, where D is your private key. Okay, so by using that private key, the receiver will be retrieving the plain text. Okay, so if it is like any unauthorized person, okay, see in this ciphertext, having this ciphertext, the unauthorized person is not able to decrypt it. Okay, so since the ciphertext has to be decrypted with the private key only. Okay, and since the private key is only known to Bob, no other person will be able to decrypt the ciphertext. Okay, so for any unauthorized person to decrypt the ciphertext, he requires the private key, and since Bob keeps the private key as secret and it is not known, so the unauthorized person is not able to decrypt the ciphertext. Okay, so that is the concept of this RSA algorithm, where this is your encryption process. This is the encryption process, where in the encryption process we will be using the formula C equal to P to the power of E mod N. Okay, and whatever the ciphertext that we will be getting, we will be sending to the receiver, and this is the decryption process. Okay, where in the decryption process, the receiver will be using his private key and applying that formula, he will be decrypting the message. Okay, and similarly he will be generating the private and public keys. Okay, for generating that private and public keys, so this is the key generation algorithm. Okay, so for generating that public and private keys, this is the key generation algorithm. Okay, So here what the receiver will be doing is that, so he will be selecting P comma Q. Okay, he will be selecting two large prime numbers. P, Q are the two prime numbers, and he will be selecting two large prime numbers. Okay, P comma Q, and then he will be calculating the n value, n equal to P into Q. Okay, and then he calculates the Gaussian function phi of n. Okay, so where phi of n is equal to this P minus 1 into Q minus 1. Okay, so after calculating the Gaussian function phi of n, so here the person who is generating that e, he has to select an integer e. Okay, after that we have to select an integer e, and such that so we have to select an integer e such that GCD of this phi n comma e is equal to 1. Okay, so we have to select an integer e such that GCD of phi n comma e is equal to 1. After selecting that integer, we will be calculating the d. Okay, where d is equal to e inverse mod phi n. That means that whatever the d that is you are calculating, that is a inverse, that is a multiplicative inverse to e. Okay, so after generating that d, okay, now the public keys will be, e comma n, and the private key will be d comma n. Okay, so see here this e and d are inverse to each other. Okay, so now what he will be doing is that he will be announcing this public key and he will be keeping the private. Okay, so that is the key generation algorithm. After generating these public and private keys, so here, what the sender will be doing is that the sender will be doing the encryption. So here, what is the encryption process? The encryption process is that, for suppose M is your plain text. Okay, suppose M is your plain text, and then how you will be getting the ciphertext? You will be getting the ciphertext by saying C equal to M to the power of E mod N, where E comma N are your public key. Okay, by using the public key and taking the message by applying M to the power of E mod N, you will be getting the ciphertext. Okay, and similarly decryption process. So for decryption, what the receiver has to do is that the receiver has to use the private key. Okay, so first he has to take the ciphertext. Whatever the ciphertext the sender has sent, so here the receiver has to take that ciphertext, and to that ciphertext he has to apply the private keys by using C to the power of D mod N. With that he will be getting the plain text. Okay, so that is about the RSA algorithm, key generation algorithm, encryption process, decryption process. Okay, so this is one example of that RSA crypto system. Okay, so where here the Bob, so here the Bob is generating the keys here. Okay, so here the Bob is doing the key generation. Okay, he is selecting two prime numbers. As we have said that we have to select two prime numbers P comma Q. Okay, so here he will be selecting two prime numbers 7 and 11. Okay, and then he will be calculating n. Okay, so next after selecting this P comma Q, we have to calculate n. So where n is equal to P into Q. Okay, so that is your n, and then he is calculating n, where n equal to P into Q, that is 11 into 7, 77. Okay, after calculating n, what we have to calculate? We have to calculate phi of n. Okay, so after calculating n, this is the second step. After calculating n, we have to calculate phi of n. Okay, so and then your phi of n will be 7 minus 1 into 11 minus 1. So 7 minus 1 is 6, 11 minus 1 is 10. So 6 into 10, that is equal to 6. Okay, so our phi of n is 6. Okay, now he chooses two exponents. Now what he has to do is that he has to choose E and D. Okay, so he has to choose E and D. Now that is your phi n. After doing that phi n, what he has to do is that he has to choose E and D such that E and D are multiplicative inverse to each other. Okay, so here already we have said here he has to choose E such that GCD of phi of n comma E is equal to 1, and he will be calculating D. That means that he has to choose two integers E and D such that both are inverse to each other. Okay, so that is what he chooses E. Okay, here he is choosing E to be 13 and D to be 37. Okay, he is choosing E as 13 and D equal to 37 such that E into D mod 6 is 1. Okay, already we have studied multiplicative inverses where if we are multiplying two elements and we are doing a mod operation, if we are getting a remainder of 1, that means that these two elements are multiplicative inverse to each other. Okay, so if we are multiplying two elements and then when we do mod operation, if you are getting a remainder of 1, that means that these two elements are inverse to each other within this field. Okay, so here we have chosen that one, that way only. Okay, we have chosen E13, D37 such that both are multiplicative inverse to each other. Okay, that means that E into D mod 60 is equal to 1. Okay, that is what we have said here. This is what is. Okay, so D is congruent to E inverse mod phi n means that, so E into D mod phi n is equal to 1. So we have to choose E and D such that E into D mod phi n is equal to 1. Okay, so here in this example he has chosen E to be 13 and D to be 37 such that both are multiplicative inverse to each other. Okay, so in that way he has generated the keys. So here the public key will be like 13, comma 77. Okay, what is the public key here? The public key will be 13, comma 77. Okay, and what is the private key? The private key will be 37, comma 77. Okay, so this is your public key and this is your private key. Okay, so after generating the public key and private key, he will be announcing his public key to Alice. So where here what the Alice has to do, it has to use this public key to encrypt the message. Okay, so here Alice wants to send a plain text file. Okay, so here Alice wants to send a plain text file to Bob. So what she has to do is that she has to encrypt this file by using this public key. So since our formula, what is our formula for encryption? Since the formula for encryption is C equal to m to the power of E mod n. Okay, so our encryption formula is C equal to m to the power of E mod n. Okay, so that is what we have done here. So C equal to m. So what is your plain text? Plain text is 5. So m to the power of E. So what is your E? E is 13. Okay, public key is 13. 13. 5 to the power of 13 mod 77, which is equal to 26. Okay, so our ciphertext is 26. So here he has done 5 to the power of 13 mod 77. Okay, 5 to the power of 13 mod 77, which he will be getting as ciphertext as 26. Okay, so next, so here this whatever the ciphertext, that 26 is sent to the Bob. So now what the Bob has to do? The Bob has to decrypt. Okay, so for decryption, so this is the decryption process. Okay, so now the Bob is going to do the decryption. So this is the decryption process where m equal to C to the power of D mod n. Okay, so this is the decryption process where C, what is C? C is the ciphertext. Since our ciphertext is 26 to the power of private key. Okay, so what is your private key? The private key is 37. Okay, since the private key is 37, 26 to the power of 37 mod 77, which we will be getting 5 mod 77. So he has retrieved the plain text file. Okay, so he has retrieved the plain text file which Alice has sent. Okay, so that is about the RSA crypto system for encryption and decryption process by using the public key crypto system. Okay, so and similarly we are having another crypto system called as the wrapping crypto system. Okay, so here this wrapping crypto system does the encryption. Okay, so it performs the encryption by doing C is congruent to P square mod n. Okay, by squaring the plain text, by doing the square of the plain text and doing the mod n operation, we will be getting the ciphertext. And how the decryption is done? The decryption is done by taking the square root of the ciphertext. Okay, so since the encryption is done by squaring the plain text, the decryption is done by taking the ciphertext by taking the square root of the ciphertext. Okay, so that is the encryption process and decryption process, where the encryption is done by squaring the plain text and the decryption is done by taking the square root of the ciphertext. Okay, so here key generation. Coming to the key generation. Okay, so here for generating the keys, here we have to choose two large prime numbers P and Q in the form 4k plus 3 and P not equal to. Okay, so whatever the prime numbers that you are selecting, those two prime numbers should be of the form 4k plus 3. Okay, and those two prime numbers should not be equal, and these two prime numbers should be large. Okay, after that we will be calculating this n. Okay, after that we will be calculating n, where n is equal to P into Q. So after that we will be getting the public key. Okay, so our public key will be n and our private key will be Q comma n, where the public key will be announced and the private key will be kept as secret. Okay, so that is our key generation. After generating this key, how we will be doing the encryption process? We will be doing the encryption process by saying C equal to P square mod n. Okay, so since n is our public key, see here since our n is public key, the encryption process can be done by using the public key. Okay, so this is the encryption process where we will be taking the plain text. Okay, so here P is the plain text. By squaring the plain text and doing mod n, where n is our public key. Okay, by using the public key and squaring onto the plain text, we will be getting the samples. Okay, and similarly for decryption process. Okay, since decryption, already we have said that decryption is the square root C to the power of 1 by 2, or we can say square root of C. Okay, since the decryption is the square root of C. Okay, so here since it is a square root, we will be having the square roots in plus and minus. Okay, so that is what we have done here. For taking that square root, they have taken like P plus 1 by 4. Okay, so instead of directly taking the square root, they have taken it out in this form. Okay, where a1 implies plus, since it is a square root, we will be having plus form and minus form, C to the power of P plus 1, where P is our private key. Okay, so here P is our private key. Since we have to decrypt by using the private keys, so we will be taking C to the power of P. P is our private key plus 1 by 4 mod 2. Okay, so and similarly A2 also, 1 is in plus and 1 is in minus, and similarly we will be taking B1, B2 also. So where B1 and B2 that we will be taking by using the Q values. Okay, by using the Q private key, we will be getting the B1, B2 values in plus and minus. Okay, and by taking the another private key P, we will be getting A1 and A2. Okay, after that we will be applying the Chinese remainder theorem. Okay, so after that we will be applying the Chinese remainder theorem. Okay, already we have discussed the Chinese remainder theorem, where by using the Chinese remainder theorem, you will be getting your P1 value. Okay, this Chinese remainder theorem is applied on A1, B1 and private keys P comma Q. And similarly A1, B2, P comma Q, A2, B1, P comma Q, A2, B2, P comma Q. All the combinations. Okay, so and then we will be returning P1, P2, P3, P4. Okay, so here this Rabin crypto system is non-deterministic. Okay, so it is non-deterministic means that it is not giving the exact value. So see here, when you are like decrypting, you are getting 4 plain text. You are not getting exactly 1 plain text. When you see your RSA algorithm, you will be getting only 1 plain text. Okay, so if you take your RSA algorithm, so your plain text is that like you are getting plain text is equal to 5. Okay, you have not got like P1, plain text 1, plain text 2, plain text 3. So here the plain text is 5, which is a deterministic, means that it will be exactly giving the plain text. Okay, where this is not like this Rabin crypto system is non-deterministic. Okay, it is a non-deterministic because the decryption creates 4 plain text. Okay, so here the decryption is creating 4 plain text, and one of these plain text will be the exact plain text. Okay, so the original message can be P1, the original message can be P2, or it can be P3, or it can be P4. Okay, so any one from these 4 can be your plain text. Okay, so So that is about the Rabin crypto system. Okay, so where decryption process, you will be applying the Chinese remainder theorem and you will be getting 4 different plain text, and one among these, one will be your plain text. Okay, so that is why it is said to be non-deterministic. Okay, so that is about the Rabin crypto system. Okay, so next crypto system that we are going to study is your algorithm crypto system. This algorithm crypto system is based on the discrete logarithm problem. Okay, so where here key generation, this is our key generation. Okay, where here you have to select a large prime number. Okay, you will be selecting a large prime number P, and we will be selecting D to be a member of the group. Okay, we will be selecting D to be a member of the group Z. Okay, ZP, that is set of integers with the prime numbers. Okay, set of residue modulo in terms of prime numbers. Okay, and then we will be selecting E1. So and then we will be selecting E1 to be a primitive root in the group G. Okay, so and then we will be getting E2. So we will be getting E2. So by taking E1 to the power of D mod P, and then we will be getting the public key as E1, E2, P, and we will be getting the private key as D. Okay, so this is how you will be doing the key generation, where you will be having the public keys as E1, E2, P, and you will be having the private key as D. Okay, where you will be deriving E2 by taking E1 to the power of D mod P, and where this D and E are the elements in the group G. Okay, so and this is your encryption process. Okay, so for encryption you have to select a random integer R in that group. Okay, so in that set of residues with multiplicative inverse ZP. Okay, the multiplicative inverse ZP. Okay, in that multiplicative inverse ZP, we have to select a random integer R, and then we will be calculating the 2 cyphers. Okay, so since we are having like 2 public keys E1 and E2. Okay, since we are having 2 public keys E1 and E2, so we will be generating like 2 ciphertext C1 with E1 as a public key and R as a random integer. Okay, and similarly C2 P into E2 to the power of R mod P, and these C1 and C2 are your ciphertext that are sent to the receiver. Okay, so now this is the decryption process, where the decryption is done by using the formula. Okay, by using this formula, the decryption will be performed. Okay, so that is the algorithm decryption process. This is your decryption process. Okay, and this is your encryption process, and this is your key generation process. Okay, where in algorithm key generation we will be generating 2 ciphertext. Okay, and from these 2 ciphertext we will be getting the plain text. Okay, so that is about the algorithm crypto system. Okay, so next one is your elliptic curves for real numbers. Okay, so here elliptic curves over real numbers uses a special class of elliptic curves of the form y square equal to x cube plus ax plus b. Okay, so here whatever the elliptic curves that you are having, that will be of the form y square equal to x cube plus ax plus b. Okay, so here you have to take some real numbers as x and y values. Okay, so here you have to take x and y values, and based upon that x and y values we will be drawing the curve line. Okay, so suppose here we define the set as points on the curve, where each point is a pair of real numbers. Okay, so for example, the set E for the elliptic curve x square, the set E. Okay, the set E for the elliptic curve y square equal to x cube minus 4x. Okay, so this is my elliptic curve. Okay, already I have said. So this elliptic curve should be of the form this one. Okay, so of the form this one means that here your a value is equal to minus 4 and b is equal to 0. Okay, if you take a as minus 4 and b as 0, then you will be getting elliptic curve of this form, that is y square equal to x cube. Since a is minus 4 into x, since b is 0, you won't do it. Okay, so here by taking a equal to minus 4 and b as 0, you will be getting an elliptic curve of the form y square equal to x cube minus 4x. Okay, so now taking this curve. Okay, now taking this curve, I have to create a set of points on the curve. Okay, so taking this equation. Okay, taking this equation, I have to define. Okay, taking this as the equation, I have to define a set as the points on the curve. Okay, where each point is a pair of real numbers. Okay, whatever the number we are getting, those should be a pair of real numbers. Okay, so for example, I have taken like x equal to. Okay, so I have taken like x equal to 2. Okay, so this is your x value. Okay, so my x is equal to 2. Then what will be my y value? Okay, so x is equal to 2 means that 2 cube. 2 2's 4, 4 2's 8. This will be 8. And this will be again 4 into 2, 8. So what is my y value? The y value I am getting is 0. Okay, so similarly when I am taking x as 0. Okay, so taking x as 0. Since my equation is y square equal to x cube minus 4x. Okay, if I am taking x as 0. So 0 means 0 minus 0, my y value will also be 0. So this is my y is also 0. Okay, similarly if I am taking x as minus 2. Okay, so if I am taking x as minus 2, then again minus 2 cube. Okay, minus 2 cube minus 4 into minus 2. So again I am getting 0. So I am getting y as 0. So similarly if I am taking x as 10, I will be getting y as 30.98. Okay, so since it is like square root, y square. Since it is like y square, it is like y square. When you take square root, you will be getting it plus and minus. Okay, so you can take like this also. Okay, so in that way we will be defining a set. Okay, so here for each x value, we will be calculating the y value, and with this x and y values we will be plotting a curve here. Okay, so here we will be plotting a curve and we will be getting the curves like this. Okay, taking this x value and y value, so this is like your x values and this is like your y values. Taking this x and y values, you will be plotting, if you plot these values, you will be getting the curves. These are said to be like elliptic curves. Okay, so elliptic curves over real number. So these elliptic, first for doing these elliptic curves, we require these two curves. For getting these two curves, we have to take the equation of this form. Okay, the equation should be of this form. If I take a equal to minus 4 and b equal to 0 on that equation, if I take a equal to minus 4 and b equal to 0 on this equation, I will be getting a equation of this form. Okay, so after that, taking different x values, I will be taking different y values. Okay, taking different x values, I will be getting different y values. Okay, like taking x equal to 2.0, taking x equal to 2.0, I will be getting y value. And similarly, taking x as 0, I will be getting y value. Taking x as minus value, again I will be getting another y value. Okay, so in that way, taking different x and y values, I will be getting a set of points. Taking different x values, from that I will be getting y values, and plotting those x and y values, I will be getting the curve like this. Okay, so this is said to be the elliptic curves. Okay, so now coming to the operations. Okay, so now coming to the operations, how to perform operations on these elliptic curves. Okay, so here these elliptic curves take a different operations. Like here also we will be having an addition operation. We will be having a doubling a point. Okay, but for doing that operations, we are having a different concept here. Okay, the specific property of a non-singular elliptic curve allows us to define an addition operation on the points of the curve. Okay, so we will be defining like an addition operation on the points of the curve. Okay, so here we have to take 2 points on the curve. Okay, taking 2 points on the curve, okay, taking 2 points on the curve, we can define an addition operation. Okay, so we need to remember that the addition operation here is different from the operation that has been defined for integers. Okay, so it is not like simply adding two numbers. Okay, so it takes a different, okay, where the operation is the addition of 2 points on the curve to get another point on the curve. Okay, the operation is here our addition operation. Okay, so here our addition operation, the operation is the addition of 2 points on the curve to get another point on the curve. Okay, suppose here for example, these are the 2 points I want to add, P and Q. Okay, P and Q are the 2 points I want to add, and the resulting point is your R. Okay, and this resulting point should be also another point on the curve. Okay, you have to remember that taking 2 points on the curve, the resultant that you will be getting, that should be another point on the curve. Okay, so here taking P equal to x1 y1 and Q equal to x2 y2. Okay, and let R be your x3 y3. Okay, so here I have taken 2 points. So suppose my 2 points are these on the curve. Okay, already we have said that taking 2 points on the curve. Okay, I have taken the 2 points P and Q on the curve. One is my P, okay, and another one is my Q. Okay, so this one is my P and another one is my Q. Now I want to add these 2 points. Okay, so one point I have taken on this curve P and another point I have taken on this curve Q. Now I want to add P plus Q. Okay, to add P plus Q, what I have to do is that I have to draw a tangent line that goes through this P and Q. Okay, so here like this. Here they have drawn like a tangent line. Okay, so we will be drawing a tangent line such that it intersects the other curve. Okay, so here I am drawing a tangent line such that it is intersecting another curve, and the reflection of this, okay, will be my resulting point. Okay, so here what is your P plus Q? So here the addition operation is different. Okay, so here in this elliptic curve cryptography, if you want to add 2 points on the curve, okay, if you want to add 2 points on the curve, it is not a simple addition. Okay, it is not a simple addition. What you have to do is that if you want to add these 2 points, you have to draw a tangent line that goes through these 2 lines, and such that it intersects at the other curve. Okay, and if wherever it is intersecting, from there you will be taking a reflection. Okay, so from there you will be taking a reflection, and this R will be your P plus Q value. Okay, so this R will be your P plus Q value. Okay, so taking every time, so if you want to add taking those 2 points, drawing a tangent line and reflecting the 2 on the other side of the curve is very difficult. For that, what they have done is they have derived the formulas for you. Okay, so they have already derived the formulas based upon this tangent line. Okay, since this is a tangent line, we will be calculating the slope of this line. Okay, first to know this R value, what we have to do is, okay, so first we have to calculate the slope for this line. Okay, so to get the R value, first we have to calculate the slope for this tangent line. Okay, so the slope is given by lambda equal to, already you know the formula for the slope of a line, y2 minus y1, x2 minus x1, where this x1 y1 and x2 y2 are the points on P comma Q. Okay, so and then you will be getting the R. Okay, and you can get the R value, resultant R value, by using x3 equal to, by using the formula lambda square minus x1 minus x2 and y cube equal to lambda x1 minus x3 minus y. Okay, so that is adding 2 points on the curve, and the whatever the resulting you will be getting, that should be also a point on the curve. For doing that, what we have to do is that we can take any 2 points on the curve. For example, I have taken one point here and another point here. I want to add these 2 points. Okay, to add these 2 points, what I have to do is that I have to draw a tangent line passing through these 2 points. Okay, so such that it intersects the other curve. Okay, and then from there I have to take a reflection. By doing that, I can get the addition of these 2 points. By doing that, I can get the addition of these 2 points, that is our R. Okay, so here for this they have given a formula. By simply placing the values in this formula, you can get that R value. Okay, so since here we are having a tangent line, first we have to determine the slope for the tangent line. That is, slope is given by lambda. Here your lambda is nothing but the slope. Okay, first we will be calculating the slope, and after calculating the slope, we will be getting the R as x3 equal to lambda square minus x1 minus x2. Already we know your P and Q values. Okay, already we know our x1, y1, x2, y2 values. Placing those x1, x2, y1, y2 values. Okay, and taking that slope value, we can get that x3 and y3, which is nothing but the resultant of your addition operation. Okay, so that is the addition operation on elliptic curve. Okay, this is the addition operation on the elliptic curve. Okay, so and this is your doubling the point. Okay, so and this is said to be the doubling the point. Okay, so this is like doubling the point. So previous one is your addition. Okay, so addition of 2 points. P and Q are 2 different points. Okay, P and Q are 2 different points on the curve. Okay, adding these 2 points, we will be getting R. For adding these 2 points, we have to use these formulas. We will be getting your R value. Okay, so similarly, if you want to double the point, okay, if you want to double the point, then in that case, what we have to do that, here suppose the point P is on the curve. Okay, so here the P is a point on the curve. So I am taking a point P on the curve, and through this point again I am drawing a line such that it is intersecting the other curve at minus R, and from this minus R I am doing a reflection, and whatever the R value that I will be getting, that will be the resultant of your doubling the point. Okay, so R is the resultant of doubling the point, or we can say R is equal to 2P in the sense P plus P. Okay, so here for this also we are having the formula here. Since here also we are drawing a line here, for that line we will be calculating the slope here. So the slope will be lambda equal to 3x1 square plus a 2y1. Okay, after calculating that slope, we will be getting this R value. Okay, we will be getting the R value by using those formulas. Okay, so that is the doubling the point, where in the doubling the point you will be taking a point P on the curve. From this point P you will be drawing a line such that the line intersects the other curve at some point. Okay, so at that point where the line is intersecting, you will be taking a reflexive point, that is nothing but your resultant of your doubling the point. Okay, so this is said to be doubling. Okay, so this is said to be doubling the point. Doubling the point, that is 2, or we can say P plus P. Okay, so where the third operation. Okay, coming to the third operation, that in the third case. Okay, so this is the third case where the 2 points are additive inverse of each other. Okay, so here the 2 points are additive inverse to each other. Okay, so the 2 points are additive inverse of each other as shown in figure here. Okay, if the first point is like P x1 y1 and the second point is Q x1 comma minus y1. The line connecting to the 2 points do not intersect the curve at the third point. Okay, so if we see here, suppose like I'm adding 2 points. Okay, I'm adding 2 points that are additive inverse to each other. Okay, suppose I am adding these 2 points that are additive inverse to each other. One point is P and this is minus P. Okay, but here these P and minus P are additive inverses to each other. Okay, if I want to add these 2 points, then what I am getting is that I should get an infinity. Okay, if I am saying like, or we can say I should get an identity element. Okay, so suppose 2 is my element. Okay, and the additive inverse for this 2 is minus 2. Okay, when I am doing 2 minus 2, what I am getting? I am getting 0. Where 0 is like additive identity. Okay, so 0 is like additive identity. So similar to this. Okay, so similar to this here also, when we are taking one element and another as the additive inverse of that element. Okay, what I should get? I should get an identity element. Okay, so here also suppose this is my elliptic curve. So here I have taken one point as P and another point as minus P. Okay, since and one is P and another is minus P. If I am drawing a line here, okay, if I am drawing a straight line here, so since it is not intersecting the other curves. Okay, already we have seen like here when we are drawing a tangent line, when we are drawing a tangent line or when we are drawing a line, it is intersecting at another curve. Okay, but here in this case, whatever the line we are drawing, it is not intersecting at any point. It is just going for infinity. Okay, it goes below like infinity. Okay, so here that is what he is saying, the line connecting the 2 points. Okay, the line connecting the 2 points do not intersect the curve at the 3rd point. Okay, whatever the line that we are drawing on these 2 points, that are not intersecting on the other curve. Okay, so that are not intersect the curve at the 3rd point. Okay, mathematicians say that the intersecting point is at infinity. Okay, so since it is not intersect the curve at the 3rd point, mathematicians say this as the intercepting point is at infinity, and they define this O as the point at infinity or 0 point. Okay, which is nothing but the additive identity of the group. Okay, so this is said to be the additive identity of the group. Whatever this O or whatever the 0 that we are getting, that is said to be the additive identity of the group. Okay, so adding 2 points which are additive inverse to each other. Okay, adding 2 points which are additive inverse to each other, the result will be like an infinity or 0 point. Okay, so sometimes it is said to be the additive identity. Okay, so how you will be getting this additive identity? You will be drawing a straight line by passing through these 2 points. Since this line is not intersect the curve at any 3rd point, so the mathematicians take this as the line is going to infinity, and that infinity is termed as 0 identity or additive identity of the group. Okay, so that is the third case in our elliptic curves. Okay, so that is okay. So this is the 3rd case of our elliptic curves over the real numbers. Okay, where we have seen that where elliptic curve. Okay, where elliptic curve takes the values over the real. So the elliptic curve takes the equation of this form, where like if you take a equal to minus b, a equal to like minus 4 and b equal to 0, you will be getting equation of this form. Okay, taking different x value, you will be calculating different y values. Okay, taking x value, you will be applying this x value on this formula, you will be getting the y values. Okay, so this pair, by using this pair, you will be these pairs, you will be drawing the curves on the you will be getting the curves. Okay, by taking these pairs and plotting, you will be getting the curves. Okay, so in this crypto system, whatever the points that you are taking on the curve, okay, so whatever the points that you are taking on the curve, that will be having a different arithmetic operations. Okay, so arithmetic operations like whatever the addition operation that you are doing, whatever the doubling that you are doing, what are the additive inverses that you are doing, that will be having a different operations. Okay, so like this is like addition of 2 numbers. Okay, so if you want to add 2 points on the curve, okay, if you want to add 2 points on the curve such that the resultant should also be a point on the curve. Okay, taking 2 points on the curve, after adding it, you will be getting a third point, and the third point should be also a point on the curve. Okay, to get that, what you have to do is that you have to calculate first the slope. Okay, so you have to calculate the slope of the line. After that, you will be calculating the x3 and y3 coordinates. Okay, so these are your P and Q values. Taking P and Q values, okay, on points on the curve. Taking P and Q points on the curve, if you draw a tangent line such that it intercepts on the other curve. So, and taking the reflexive point, you will be getting the R value. Okay, so here since it is like a line going through that, for that line we will be calculating a lambda value, and from that we will be determining this x3 and y3 points. Okay, so similarly for doubling the point also. Okay, so similarly for doubling the point also, and similarly for taking the 2 points as the additive inverses of each other. Okay, so these are the 3 operations that are done on the elliptic curves. Okay, so that is nothing but the adding 2 numbers, doubling the point, and adding 2 points that are additive inverses to each other. Okay, so that is about the elliptic curves, which comes under the public key crypto system. Okay, so those are the different public key crypto systems that you have studied in this class. Those are your RSA crypto system, Algamel crypto system, Rabbit crypto system, and elliptic curve crypto system. Mathematics of cryptography. Okay, so a prime is divisible. Okay, so mathematics of cryptography. So here, like since already you have studied your RSA algorithms. Okay, so RSA algorithm are all these algorithms takes prime numbers. Okay, so they will be taking 2 large prime numbers, or they will be selecting 2 prime numbers. Okay, so here in CNS, okay, in cryptography, prime numbers plays a very vital role. It plays a very important role. Okay, so here what is a prime? A prime is divisible only by itself and 1. Okay, if a number is divisible by itself and 1, then it is said to be a prime number. Okay, so how to check for the primeness? Okay, how to check for the primeness of a number? Okay, given a number n. Okay, given a number n, how can we determine if n is prime? Okay, so the answer is that we need to see if the number is divisible by all primes less than root n. Okay, so you have to calculate first root n. After calculating the root n, then you have to check whether all the prime numbers less than that root n is divisible. Okay, so let's see one example here. If 97 a prime, okay, is 97 a prime. So here the solution is that first you calculate root 97 and you take the floor for that root 97. The floor for the root 97 is 9. Okay, so and then you have to take the numbers less than 9. Okay, the primes. Okay, then you have to take the prime numbers less than 9. Okay, so here after calculating the square root of that 97 and taking the floor of that 9, you have to find all the numbers, okay, all the prime numbers less than 9. Okay, so here the prime numbers less than 9 are your 2, 3, 5 and 7. Okay, the prime numbers less than 9 are 2, 3, 5 and 7. Now we need to say if 97 is divisible by any of these numbers. Okay, so we need to see if 97 is divisible by any of these numbers. If it is not, then we will be saying 97 is a prime. Okay, so we can see here that we can see here that so these 2 is not divisible by 97. 3 is also not divisible by 97, and 5 and 97 are also not divisible. So we can say that 97 is a prime. Okay, so that is one method. So for checking whether a number is prime, okay, so first we have to take a square root of that 97 and we have to take the floor, and then we have to take prime numbers less than 9. Okay, so the prime numbers less than 9 are your 2, 3, 5 and 7. Okay, and then we have to check whether these numbers are dividing like is divisible by 97. Okay, since all these numbers are not dividing 97, or we can say not divisible, so we can say 97 is a prime. Okay, and similarly another example is 301 a prime. Okay, so here also we will be taking a square root and floor. We have got the number like 70. Okay, and then we have to take all the primes less than 17. Okay, so here the primes less than 17 are 2, 3, 5, 7, 11, 13 and 17. Okay, so here the numbers 2, 3 and 5 do not divide 301. They are not dividing 301, but 7 divides 301. Okay, but here this 7 divides 301. So that means that 301 is not a prime. Okay, so that is one method for checking the primality. Okay, so that is one method for checking the primality of a number. Okay, so similarly the next concept here we are having is the Euler's phi function. Okay, so called as phi m. Okay, which is sometimes called the Euler's torsion function, plays a very important role in cryptography. Okay, so here the Euler's torsion function is given like if it is phi of 1 is 0. Okay, if it is a prime number. Okay, so phi of p means p minus 1. If p is a prime, then the Euler's torsion function will be p minus 1. Okay, so if it is like some m and n, where m and n are relatively prime. Okay, phi of m into n means that phi of m into phi of n. Okay, and similarly phi of p to the power of e is equal to p to the power of e minus p to the power of e minus 1 if p is a prime. Okay, so these are some formulas like that we are having for the Euler's torsion function. Okay, so let's see some examples. Okay, so what is the value of phi 13? Okay, what is the value of phi 13? Since 13 is a prime. Okay, since 13 is a prime. Okay, so already we have said since 13 is a prime. Okay, so here, so if it is a prime, okay, if it is a prime, then we can simply say p minus 1. Okay, so according to your second condition, okay, according to your second condition, since that 13 is prime, we will be simply saying p minus 1. Conditions, 2 slides. Okay, so that means since this p is a prime, so 13 minus 1, 12. Okay, so and similarly what is the value for 10? Okay, so here 10 can be written 2 into 5. Okay, so 2 into 5. Okay, so this comes under the your second condition. Okay, like 2m into n. Okay, when it is m into n, you will be saying phi of m into phi of n. Okay, so it is phi of m into phi of n. So that is the case here also, since here 2 into 5, where 2 and 5 are relatively prime. Okay, so in that case you will be saying phi of 2. So what is phi of 2? Since 2 is prime. Okay, since again 2 is prime, so we can say phi of p minus 1. That is 2 minus 1. Okay, so this phi 2 into 5. Since again this is your prime number. Okay, so since again it is prime number, you can say phi of p minus 1. That is your 2 minus 1. And again since it is also a prime, so you can say phi minus 1. That is 1 into 4. That is 4. Okay, so that means that 1 into 4. That means that we will be getting 4. Okay, so here like you will be applying the second and third rule. Okay, so you will be applying second and third rule for getting the Euler torsion function. Okay, so and this is another example. What is the value of phi 240? Okay, since this 240 can be written in factors in form of prime numbers. Okay, so this is like your condition 4. Okay, so if you take like, okay, so this is like your condition 4. Okay, so condition 4, phi of p to the power of e. If it is like this, okay, so we will be writing, okay, so if it is phi p, we will be writing p to the power of e minus p to the power of e minus 1 if p is prime. Okay, so here 240, you can write 240 as 2 to the power of 4 into 3 to the power of 1 into 5 to the power of 1. Okay, so then by using that, phi of p to the power of like whatever e you are having, that you will be saying p to the power of e minus p to the power of e minus 1. Okay, so here 2 to the power of 4. So 2 to the power of 4 means that, so p to the power of e, that is 2 to the power of 4 minus p to the power of e minus 1. E minus 1 means 2 cube. Okay, so similarly for this also, and similarly for this you will be getting 6 part. Okay, so and similarly the another example, like when you are having phi of 49. Okay, so 7 into 7, since you can write whether phi of 7 into phi of 7 equal to 6 into 6, 36. This is wrong. Okay, since 49 has to be written in this form. 49 is equal to 7 square. Okay, since 49 is equal to 7 square, okay, so it is like 7 square, since it is again of the form p to the power of e. Okay, 49 can be written in 7 square. So since 7 is prime, okay, so it is of the form this form. Since it is of that form, you have to write 7 square minus 7 to the power of 1, that is equal to 42. Okay, so that is another example of your Euler-Torschian function. Okay, this Euler-Torschian function and checking the Euler-Torschian function you will be using in your RSA algorithm. Okay, thank you.